How do we get a spacecraft from a low Earth orbit that starts off inclined into a geostationary orbit that has zero inclination in a nearly 24-hour period? Well, let's look at this cardboard cutout that will indicate some of the issues that we have in getting from the inclined orbit. When we launch from Cape Canaveral, and we can assume that this little circle here represents the circular orbit, the low Earth orbit that we start with, the lowest inclination we can have is 28.5 degrees, which is the latitude at Cape Canaveral. If we launch and keep the spacecraft in that inclined orbit and launch when we are at a node, that is when we're in the equatorial plane, which is represented by this orange plane, then we can get on our Hohmann transfer orbit all the way out to the distance of 42,000 kilometers, which is the radius of a geostationary orbit. At this point, we can then do an inclination change that will zero out the orbit's inclination for a far lower value than if we corrected that inclination in the low Earth orbit, where the velocity is much higher. So when we're out here at apogee, we can change from the inclined orbit represented by the white paper with a delta V that goes nearly straight down and is a much smaller delta V. At that point at apogee, we are in the same plane as the equator, and we can do a circularizing maneuver, which will then put us into the nearly 24-hour orbit that is the geostationary orbit. Let me explain this in more detail on the blackboard. So what do we mean by a geostationary orbit in the first place? Well, GSO is an orbit that takes one sidereal day to complete. And a sidereal day is just a little under 24 hours. It's 23 hours, 56 minutes, in 4 seconds. That's the time it takes the Earth to rotate inertially one time. So we want to get into this orbit starting from a Leo orbit that's inclined at 28.5 degrees. Now let me mention that the geostationary orbit means that from the ground, the satellite in such an orbit will appear fixed in the sky. It will not move in direction. So if you point an antenna towards that satellite, the antenna can remain fixed on the ground and will always be pointing at it to either transmit information up or receive information coming down. So that means a geostationary orbit must be circular and have an inclination of 0. This is different than a geosynchronous. This is different from a geosynchronous orbit, because a geosynchronous orbit means you have this period of one sidereal day, but you can have non-zero eccentricity and non-zero inclination. If you have non-zero inclination, what you will observe in a geosynchronous orbit, or GEO, is a north and south oscillation over a period of 23 hours and 56 minutes. If it is eccentric, you will also see an east-west variation because of the eccentricity, although on the average it will still remain in the sky over a sidereal day. So how do we get there? Well, here we imagine launching from the Earth from Cape Canaveral, and as we mentioned, we're going to be in an inclined orbit of 28.5 degrees, which is the minimum inclination that we can get at Cape Canaveral. We launch into this low Earth orbit, so there's our Leo at 28 degrees, 28.5 degrees. And if we were attempting to remove the inclination in this orbit, the cost to us would be fairly large, 3.84 kilometers per second. to change this inclined orbit to an equatorial orbit. So let's not make the change initially. Let's go into orbit, low Earth orbit, and when we get to this node here, that's when you pass through this inclined orbit through the equatorial plane. We'll do a maneuver there at the perigee that will take us all the way out to apogee here, and that's at approximately 42,000 kilometers. And at this point, our velocity is much lower than it was down here, and it costs less to change the inclination. So at that point, the delta V inclination change is only 0.785 kilometers per second, considerably less than the inclination change from LEO. So let's look at this other picture to get a better idea what's going on. Here we have injected the spacecraft into the Hohmann transfer that takes it out to apogee here at the 42,000 kilometer distance corresponding to the sidereal day radius that we need. And we are inclined, and we would do a maneuver that would basically be nearly straight down. And that's this maneuver that removes the inclination when the velocity is much lower. At that point, we can come back to this picture, and having done the inclination change, we can then do the circularizing burn, which is delta V of 1.48 kilometers per second. So that's the circularizing burn. And so we have a grand total. If we add these two numbers together, the total is 2.265 kilometers per second in order to remove the inclination and to circularize the orbit into the big geostationary orbit that we see here in red.